Okay, now I will start. Okay. So the vehicular automation involves the use of mechatronics, artificial intelligence, multi-agent system to assist the vehicle operator. These features and the vehicles employing them may be labeled as intelligent vehicle or smart vehicle. Vehicle using automation for difficult tasks, especially navigation, may be referred as semi-autonomous vehicle. What is autonomous car? Basically, it is an autonomous vehicle capable of fulfilling the human transportation capabilities of traditional car. It's an autonomous vehicle. It is capable of sensing its environment and navigating without human input. The history of that autonomous, first 1920s, it is a transmitting antenna. 1930, it is embedded circuits and radio controllers. 1950, detector circuits, special radio receivers, audible and visible warning devices. In 1960s, electronic controlled highways, powered and controlled by buried cables, wayside communications, relaying computer messages. This is the one of the advertisements seen in 1956 and 1957. They have predicted autonomous cars. This advertisement is inspired by so many in that particular year. So this vehicle is driving on its own and they are playing the game actually. In 1980s, laser, radar, computer vision and autonomous robotic control, off-road map and sensor-based autonomous navigation. In 90s, extensive system engineering work and research, video cameras on board and use of stereoscopic vision algorithms. In 2000, real-time control system, RFID tags. In 2010, artificial intelligence, GPS, LIDAR, 3D mapping, cameras, sensors, etc. So what is the US Department of Defense enabling autonomous vehicle technology priority? First, it should have a common architecture. It should be open and modular architecture, and it should have a standardized interfaces, and it should progress towards commercial standards, and developing a semi-autonomous mobility that should do the obstacle detection and avoidance, tactical behaviors, and man-machine interfaces. And it should have a mission payloads such as robotic manipulators, sensors, and weapons. And human interventions for mission should approach 0. As per SAE, you are already aware, there are 5 levels from 0 to 5, where 0 is no automation, 5 is full automation. What is the degree of autonomy in military operation? In military operation, these are not a standard, but initially the teleoperation is required to do the safe operations such as like a CBRN detection and some logistic employment. Those things you can use the teleoperated thing. And another approach is leader follower approach. This is basically used for counter insurgency, counter surveillance operation. This is especially useful in a J&K areas where one vehicle is going, advanced vehicle, other vehicle will be following the vehicle so that to reduce the casualty of the soldiers. And third one is autonomous vehicle. This will be required for any terrain under all weather conditions, all time, and including day and night. And that last approach is network-centric operation, where all ground vehicle, unmanned aerial vehicle, unmanned underwater vehicle will be connected. And remote control, you are already aware, direct line of sight operation of vehicle. So it will be directly control the throttle and steering. Second phase is augmented teleoperation, where you are seeing a line of sight beyond line of sight control through sensor feeds video and direct control of throttle and steering. And it should have obstacle detection, collision warning, and also stability control of the vehicle. The third is semi-autonomy, combination of autonomous navigation and shared user controls. And the fourth one is fully autonomy, no user interaction is required. And the fourth one is network-centric autonomy. See here, all are coordinating and collaborating for a common mission. Here, most of the data is high-level data fusion also occurring to make the decision. How it is made? So it is basically inspired by the living organisms. It is a basically reactive approach. A deliberative approach, brain will process the things and reason and cognitive, body will be actuate. This is a three-tiered architecture level for autonomous. First thing is you have to sense the environment, then you react and execute the thing, and again that planning, that goal and destination will be given by the world model. Based on that, you will actuate the vehicle actuators to do the required operation. So what are the modules in this autonomous system? First one is supervisory module. It is responsible for overall monitoring and supervisory control. It is having a mission planner from where, what is the source point and what is the destination point. And this is the navigation module. It will works out the route. It will having a RNDF and RDDF files, that is route network data file and route data definition file. It will take inputs on blockades, traversability, etc., and works out alternate paths. And third one is a control module. It will take commands from navigation, responsible for overall control of the vehicle. It will ensure the vehicle stability, honoring the speed and direction. A third one is, fourth one is actuation module. It will form the nearest vicinity of the vehicle control, responsible for actuation of all control, that is acceleration, brake, clutch, and gear and steering. And this is the important perception module. It will pursue the environment of the vehicle. It includes sensory organs like lidar, radar, optical camera, infrared camera. It will be quickly sense and make out static and dynamic obstacles and report to navigation. Localization model, basically it will tell the where am I. It will reports to navigation to present location using the GPS and INS sensors. This is the autonomous vehicle developed by the VRDE. So basically it is having a Velodyne 3D lidar, and the perception module will pursue the environment and send the pursued data through the obstacle map to the navigation module. Localization module will give the localization information, that is positional information, to the navigation module. That supervisory module will give the mission planner where to go. The navigation module will give the speed and yaw command to the control module. Control module will actuate the vehicle based on the vehicle dynamic parameters. So the overall architecture, it is a low level. There are a lot of components involved, stereo cameras. These are LAN, they are connected internally, LAN connector, USB connected. There may be so many horizontal lidars, vertical lidars, 3D lidars, radars, ultrasonic sensors, or basically for obstacle-free processing, environmental mapping, external sensor processing. And this is localization sensor, GPS, INS, compass, internal sensors. And there will be driver-wire system for actuation of the vehicle control, like throttle, steering, brake, and dead reckoning for vehicle position. So this is a low-level architecture. So overall architecture, where is the software? So the main software framework is Robotic Operating System (ROS) framework. It will reduce the burden of severe headaches of software housekeeping, coding. It will reduce the coding. No monolithic architecture, scalable and expandable. It works on publisher and subscribe paradigm. One PC to host ROS core, all other functionalities such as perception, localization, navigation. Other models will be considered as a nodes. It is an open source. It is a popular and favorite. This is the complete ensemble of all sensors and controller module in a continental vehicle. So now I coming to the defense application. So civilian applications are there, but in compared to civilian application, defense applications are more. But in this, we need industry cooperation for realizing of this application. First, come to the counterinsurgency and counter-terrorism roles. There is a need of mine clearance UCV, explosive ordnance and disposal UCV, and route clearance UCV, right controller UCV. For combat roles, you need a armored fighting UCV, and decoy and deception, anti-tank missile launcher UCV, sacrificial suicidal UCV, TWS UCV. For combat support role, we need a guard UCV for border protection, and RSTA, reconnaissance, surveillance, and target acquisition UCV, swarm UCV. There may be multiple UCVs are contacting for common operation. Inventory handling UCV, casualty evacuation and extraction UCV, logistic UCV, and armored engineering recce UCV, ordnance handler UCV. There is a need of follower UCV, and will be need of a target UCV. Regarding NBC disaster management roles, you need a NBC recce UCV for detection of NBC contamination, that is CBRN contamination, and you need a UCV for decontamination also, and you need a UCV for dosing and snow UCV. You need UCV for search and rescue operation. And signal roles, you need a communication relay UCV, electronic warfare UCV, electronic bomb UCV, use drop UCV. These are the so many applications are there in defense. But in this defense, other than DRDO, there is a lot of participation is required from the Indian industry. So what are the UCV developments we have carried out in VRD so far? This is the CBRN Mini UCV. This is a basically tele-operated vehicle. It is having a 4 flippers, so it can traverse in a inside and indoor and as well as outdoor. It is having a robotic manipulator for sample collection. It is having a CBRN sensors for chemical and biological detection, nuclear detection, and it is having obstacle detection capability also. This will be operated through the handheld operator for remote operation as well as teleoperation through wirelessly. And we have carried out this so many trials at our test center at National Automatic Test Center at VRD. So this is the test setup of testing of the CBRN UCV. It is for gradient 36 degrees and water obstacle up to 20 centimeter. A stair climbing from rise 18 centimeter, trade 25 centimeter, sand crossing and ditch crossing 50 centimeter, indoor operation for staircase, and pothole track at NCAT at VRD. This is a 100 mm corrugated track, and this is a robotic arm used for manipulation. That is a sample collection of a NBC contaminated zone. This is a small video clip of the CBRN UCV. This is the maximum speed, it will go 6 km/h. This is soil, it is collecting the soil from the robotic manipulator. This will collect the sample and it will bring back the sample back to the mobile laboratory for determining the contamination levels. This is a B vehicle gradient. Actual B vehicle will cross this kind of gradient 30 degrees. This is a ditch crossing at 50 centimeter. Obstacle crossing up to 25 centimeter. Obstacle detection and warning. The present status of this UCV is we are going to technology transfer to Indian industry. So this is the present status of this vehicle. And one more thing, we have carried the multiple sensor fusion using the probabilistic methods. We have used 3 different types of sensor. That is a radar. This is based on Navtech UK, and this SIG sensor from this is a 2D, and one more sensor is a 4-layer 3D lidar, and we have mounted on sensors on a Tata vehicle test platform. This is the independent occupancy map of radar, and this is the independent occupancy map of 2D lidar. This red dot shows the vehicle position, this point cloud data, and we have fused the data based on the occupancy that probabilistic methods, and this is the fused occupancy map, and this is the small video clip of the fused occupancy map. Here we have fused only lidar, radar, not video. See, you can see that this is the road, how we were mapping, and one cyclist is coming, it is pointing here. This red dot is our own vehicle. This point cloud data. This will be input to the navigation module for path planning and as well as obstacle avoidance. So coming to this autonomous UCV, whatever the system architecture we have used, there are key modules are vehicle navigation module, vehicle control module, vehicle actuation module, and vehicle perception module and vehicle localization module. The vehicle parameters, that is environment of the vehicle, will be sensed by the perception module using the perception sensor. This will sense it will give the output obstacle information, cost map, raw data, process data to the navigation module. And the localization module will collect the localization position of the vehicle using a localization sensor, and it will transmit the positional information to the navigation module. Based on this perception data and localization center, and as well as based on mission parameters from the supervisory module, that is BSM, it will generate the speed and yaw rate to the vehicle control module. So this will give the input to the vehicle actuation module based on the vehicle stability and the dynamics of the vehicle, and it will generate again the drives for actuation of the individual steering, gear, accelerator and brake commands for controlling the vehicle. This is the autonomous UC what you have realized at VRD. This is the Velodyne lidar used, and the cameras used for remote monitoring. This is a small clip you can see. Yeah. This is the inside vehicle actually that we have used at cockpit side, and he is feeding the input, that is the waypoint information. This is a driver wire system. This we have done experiment on Honda CRV vehicle. This we have tested at our National Automotive Center at VRD Aman Nagar. Coming to this autonomous UC, we have developed using that probabilistic algorithm, that is a classical algorithm. So next stage we want to go in a AI based architecture. For that we need industry participation for the perception part, especially for the obstacle classification and segmentation work and obstacle tracking, and similarly for vehicle navigation module also for that AI based motion planning and control. And the perception involves the road traffic segmentation, lane detection, pothole and bump detection. These are the critical area, because normally in urban driving you may not face these issues, but in army scenario you have to face this. So many ditches will be there, so much of vegetation will be there. So this is a very critical application for army scenario. There will be no structured roads. Okay, there will be snow, rain, and so many things. And for that you need AI-based perception system. And for local planning, you need AI-based behavioral arbitration. For low-level path planning, you have to track the oncoming vehicles, how they will go, what is their direction. You have to predict the vehicles using the AI methods, trajectory planning and behavioral prediction, and AI-based motion control you need. Basically, this kind of autonomous vehicle, maybe electrical vehicle-based operate, this can be used for uh, multi-role autonomous vehicle for combat purpose, for weapon location as well as logistics, as well as surveillance roles. You might be aware of that recently that the government of that Ministry of Defense announced that make 2 category for development of autonomous combat vehicle. Or you can also participate in that area. So that needs so much of high level of perception required. And coming to other project, there will be robotic kit for autonomous driving. So what it will does, that existing UCV configuration, what happens that conventional driving controls will be modified by drive-by-wire system, and basically it are vehicle dependent. So conversion from manned to unmanned vehicle, it will be very lengthy and complex. So what is our solution is we have to develop a modular robotic kit for automated driving. What it will consist, basically it will consist portable and modular drive-by-wire robots for driving controls. These modular drive robots can be retrofitted on any specific class of vehicle like LMV and HMV, and it may be automatic or as well as manual also we can facilitate. So it will be converted from manned to unmanned very easily. The applications basically in defense, it can be used for autonomous combat vehicles. And there is a UCV requirement from the Indian Army for UCV philosophy. They need to apply kit. With that kit, you can convert any conventional army vehicle into the remote control vehicle as well as autonomous vehicle. There is a need of this application. And there may be application, one more is robotic test driver. Basically, it will use for endurance testing like mine laying, and as well as in testing, and like in VRD, what happens that vehicles will be tested using a manual driver for high speed test and all this so much. But that is a very tiresome operation. If you give such kind of modular robots to the test vehicle, so that will helpful the efficiency of the testing. So the concept behind this is there will be modular robots will be there, like a steering robot. This can be fit on any kind of LMA class vehicles. And similarly for brake robo and steering brake robo, acceleration robo and clutch robo, and one gear shift robo. This will be plug and play. First, initially we need to do the calibration work, how much that actuator setting we will keep. After that, we'll do this operation. What is the silent features of this is, it can be configured for both LMV and HMV. And driving robots, what are concentrating? Pedal robots such as accelerator, brake, clutch, steering robot, gear shift robot, parking brake, and modes of operation will calibration. For initial calibration is required for a new vehicle. Once calibration you can do, first you will do the teleoperation maximum speed 25 km/h. Then automated waypoint navigation without obstacle avoidance in defined environment. Maximum speed you can go up to 100 km/h. Autonomous mode with obstacle avoidance, maximum speed 50 km/h on plain road. And one more is diagnostic mode. A software suite will have a perception, localization, navigation, control, actuation, supervisory, and mission planner module. The SAE level we are targeting 3 only. That communication range, 1 kilometer line of sight and 500 meter non-line of sight. Safety features, we are having health monitoring, geofencing, obstacle avoidance, emergency stop, auto stop based on software intelligence, remote operation from OCU. There will be one fail-safe brake in addition to the vehicle brake system. When vehicle brake will fail, then fail-safe brake will take over the vehicle. And there will be base station for controlling this modular robot vehicle, as well as to transmit the mission of parameters. This is the block schematic of the robotic kit. There is a pedal robot, accelerator, brake, clutch, and steering, gear, and parking. And there is a perception control. It will sense the data from the perception sensor using 3D lidar, radar, and camera. And automated driving control will take the localization sensors as well as perception data. This will give the automated driving operation for the modular driver robots. And in addition to it will transmit the information to the OCU through the wireless communication. So there is a global companies also available in this category. AB Dynamics is leading in this sector for modular robots. Basically, they will use for this testing purpose. So we are made a comparison sheet with VRD and AB Dynamics. They are having pedal robots. We are also having here. Modularity as per torque and application, one number. For acceleration, they need one number of modular robot. brake 3 numbers, they need steering 5 numbers. Basically, they will concentrate only LMV class only, whereas they will classify LMV as well as HMV class. LMV, we are considered Tata Sumo, Scorpio, Bolero, Honda CRV, Travera, van. These kind of vehicles, our modular robots can be fitted. That fail-safe brake is there, only emergency brake. In addition to the emergency brake, we are having fail-safe operation with redundant brake actuators, steering robot as gear shift robot for manual as well automatic control. Yes, parking brake is not catered in this AB dynamics, we are catered. Sensors for automation, they are having only GPS with inertial navigation. We are having GNS with RTK, LiDAR, radar, and cameras. Modes operation, remote, and limited path planning only. Whereas we have teleoperation, automation, waypoint navigation, autonomous operation. Mission planner include path planning for testing purpose. We are having mission planner greater than 60 features for ease of operation by end user. This is the first of its kind in India, robotic kit with autonomous driving capabilities. No requirement of any specialist vehicle. Any used conventional vehicle can be converted into unmanned vehicle by retrofitment of modular apply kit on a need basis. It is a dual use technology. It can be used for vehicle testing as well as defense application with the need of unmanned operation and in risky and dangerous zones to facilitate personal safety. These are the realized modular drive-by robots we have tested in Tata Sumo vehicle. This is the steering robot. This is the pedal robots, and this is in Honda CRV. I tested this modular robot. Coming to conclusion, see, compared to civilian application, so defense applications are very huge. There will be no restriction on employing a automated guided vehicles in defense application. It will act as a force multiplier, often hand and held with soldiers. It is having more teeth with C4I for command and control, communication, computers, intelligence, surveillance, and reconnaissance purpose. Thank you. Any doubts?
Thank you, Dr. Valli.
Yeah.
For being with us, for sharing your presentation. Thank you very much. Thanks a lot. Have a nice day.
Thank you.
Now coming over to Dr. Rahul Rajdan. He's from Florida Polytechnic. Conclude today's session. He doesn't need any introduction as such into the autonomous fraternity. He's a seasoned scientist and a business executive who has significant role in the world of academia, startups, Fortune 500 companies. Since 2012, he has worked to incubate ideas into reality, which has resulted into several startups. Today, active projects for the institute include avcc.net in the area of autonomous vehicle. Next, gendu.net in the area of STEM education. Over to Nitish for the video play. Thank you very much.
Hello. As I understand it, I'm your last session for the day, so let me try to make this relatively quick and efficient. First, I want to talk to you a little bit about the conference you've just participated in. So this is a kind of a pretty unique conference. It's something we call the global hybrid model. So what is a global hybrid model? We all know in the old days when we used to have conferences, everybody would fly in to one location, and that was very nice because you could have interaction with colleagues around the world that you wouldn't see ordinarily. But of course, that's expensive, and in these days of international tensions, the visas are sometimes a problem, and of course, finally, COVID really stressed out that model. And the other model is a virtual conference, where we all do this virtually, and that has its advantages, where everybody can participate very easily, but sometimes the time of day is an issue. And also, just from a business point of view, doing business development or getting people to build awareness for such a conference can be difficult. So we've come up with this interesting hybrid model. And the key thing about this model is we have a anchor location, much like the old model. We also have everything available virtually. But on top of that, we've added this idea of local physical locations, which are then driven from the local site. And this is very important because then they can emphasize what's important to them. They can also drive a local program. And yet, for the conference attendees, everything is available to them virtually. So this is really quite unique, and I think perhaps the way that conferences will go in the future, and we're, for IEEE anyway, this is the first one we've tried with this model. You know, one of the real advantages of this structure has been that now, as an example, in India, in Pune, in the center there can be a focus on local interests in the context of the global conference. So that's enough about the conference, the structure of the conference. Let's talk about the content of the conference. So, you know, AI has this new technology, this new capability, which is really changing the world. And so what the most interesting things about AI, or I should say machine learning, is you can build algorithms from data. And this is a relatively profound thing to do. Many people have looked at this and said, oh, maybe there's an analogy to this with evolution and how animals and human beings learn. And people are looking at this sort of thing. But of course, the issue is, if you're asking data, just driving data in to build an algorithm, how do you know whether the algorithm works? And the nature of this conference is to look at those issues. And you've just gone through the Pune program, but I want to tell you a little bit more about the other locations and the things that they focused on. So in the US, we have a broad program, and perhaps there's 3 important points I want to get across. One is we have keynotes coming from the government and the consumer sector. So we have a gentleman named Anant Prasad, who was the Secretary of Transportation in Florida, one of the largest states in the United States. And he's going to talk about the requirements around infrastructure that will be needed and how do you specify them, how do you fund them, and how do you verify them in a state like Florida or beyond. Another person that's going to come in is Greg Brannon. Greg is going to talk about AAA. AAA is a large consumer agency in the United States, and what they've been doing has been testing the autonomy capabilities of the cars that are on the road, such as Tesla and others. And they've been finding, interestingly enough, there are issues. They don't quite work as advertised. Well, we have a couple of people that are coming from validation powerhouses in the industry. So we have Alex, he's the CTO from TÜV Süd. TÜV Süd is the regulator, the main regulator in Germany, and a worldwide powerhouse around building validation and safety technologies. And United Laboratories, Mary from the senior VP from United Laboratories, and UL, you probably have heard of, is a powerhouse in the electronics space. So they're going to both talk about the impact of how do you build methodologies to test these validation systems. And then finally, we have in the state of Florida, where the anchor location is, there are many places which are now experimenting with autonomous vehicles. So we have the city of Jacksonville, Orlando, Miami, Tampa, all of them looking at typically public transportation shuttles. And the key company that's sort of at the center of this is a company called Beep, funded by Intel Capital, that is providing these solutions. And so we're going to have a talk about that. In the German version of this conference, we have talks from AVL, which is a large industrial software company in this space. We're going to have Taltech, this is the Tallinn Institute of Technology, talk about their shuttle that they build with open source systems in Estonia. We're going to have Mercedes and Audi talk about their needs from an OEM point of view, and then an organization called IAMTS, which is trying to pull together some commonality around testing and especially test sites around the world. in terms of providing capability for vendors to use. And finally, in the China program, they're going to source a lot of the stuff that's coming from other places. That's one of the beauties of such a hybrid structure. And Qatar, which is sort of their big testing agency, is going to give a talk about testing in China. So if you're a virtual registrant in the conference, you get access to all of this information. And that's one of the beauties of the program that I discussed, this hybrid program. And on top of that, you've of course got the physical interaction of coming to a local event, or if it's not physical, the locality encourages connection, even if it's a virtual event. So I hope you enjoyed the event. I hope you sort of can participate even after the conference with the virtual assets that the conference has built up. Take care. Bye-bye.
Thank you, Dr. Rajdan. Once again, I would like to invite Mr. Rajiv Kaushal, Chairman and Founder of Acclivis Technologies, to join us for the closing remark for the day. Over to Mr. Rajiv Kaushal.
Thanks, Anurag. Thank you very much, everyone. This has been really a hectic day, but full of excitement. We could manage to get lots of speakers from different parts of the continent. Some of them could give the knowledge which probably we must not have seen earlier. Some of the recorded sessions were the hands-on work which people were doing, and we could not accommodate them in live sessions. That's why recorded video were shown. Team Acclivis also put up lots of efforts in order to ensure that flawlessly throughout the day, without any break, the symposium should keep on going. Thank you, everyone. Looking forward to have another session soon. Best of luck.